Welcome to this explainer, brought to you by Forge College. All right, so in our last session on advanced entry point concepts, we laid down the theory. Well, today, we're actually getting our hands dirty with some real code. We're going to take a minimal Solana program template and modify it to add config options, parse instructions, and enforce basic validations, literally right at the entry point.
So how do you actually keep bad data out of your Solana program? To really nail this, we kind of need to completely shift how we think about our program's front door. I want you to picture the Solana program entry point not just as, a block of code, but as a massive, uncompromising bouncer at a super exclusive nightclub. We're essentially designing a strict security checkpoint blueprint. This bouncer has to check IDs, inspect whatever baggage people are bringing in, and just immediately turn away anyone breaking the rules, way before they even get a glimpse of the dance floor, or, in our case, the core business logic.
Okay, here's our agenda for today. We'll be covering the blueprint, wiring the configuration, unpacking the instructions, enforcing the preconditions, testing the entry point, and preparing for automation. Let's just dive right in. Starting off with Section 1, the blueprint. So, here's the high-level flow happening inside our main lib.rs file. It's a really elegant four-step process. First up, we wire the configuration to set the rules. Second, we unpack that incoming data. Third, we validate the accounts being passed in. And finally, and really only if everyone passes those initial checks, we dispatch the request to our handlers. Keeping these steps clearly separated is absolutely crucial. It drastically reduces the surface area for bugs and makes our entry points highly auditable. Moving right along to Section 2, wiring the configuration. All right, first thing on our blueprint is giving our bouncer the ground rules for the night. We do this by creating a really minimal configuration struct. It's kind of like pulling the bouncer aside and saying, hey, tonight we're in strict mode, or tonight we're in permissive mode. This simple entry config enum basically gates the behavior right there at the door. And by wiring this config up first, we safely isolate the parsing from all that heavy runtime logic that happens later on.
Next up is Section 3, unpacking the instructions.
Okay, time for the ID check. Our program needs to know exactly who's knocking at the door. In Solana, this is handled by the instruction discriminant. The discriminant is literally the ID card of the binary payload. It's just the very first byte. Our instruction.rs module looks specifically at that single byte to figure out exactly which instruction variant we're dealing with. Once it knows that, it knows exactly how to unpack the rest of the data.
You can think of this discriminant map as the actual clipboard our bouncer is holding. It's a crystal clear schematic of who gets in and exactly what baggage they're expected to have. For example, if the discriminant is a 0, boom, it's an init instruction, and we expect a very specific payload shape. If it's a 1, it's an update config instruction, which has totally different validation rules. Having all of this explicitly mapped out, that's what makes your code incredibly robust.
Now, what's super interesting here is the massive difference in the baggage these two instructions carry. An init instruction, that one brings a heavy 10-byte payload. Our program actually has to carefully use a little endian conversion just to unpack the 8-byte amount. On the flip side, update config travels super light, literally just 2 bytes. It only needs its ID card and a single mode byte. So if someone hands us an init ID card but only brings 5 bytes of luggage, well, our bouncer instantly knows they're trying to pull a fast one.
Which brings us to Section 4, enforcing the preconditions.
Right, so after checking the ID and the luggage, it's time for the pat-down. We've got to make sure they have the right keys and permissions. We literally must check our accounts array the second they walk in. We verify the array isn't empty, check if the required accounts are actually marked as writable, and look for those necessary signers. The big takeaway here, we are enforcing these preconditions before any business logic even thinks about running.
So here is the absolutely crucial point. If someone fails that pat-down, you return an explicit error. You want to hand them a polite but very firm program error.invalid instruction data or not enough account keys. That's your bouncer saying, yeah, no, get out. What you absolutely, positively must not do is panic. Panicking is like throwing a massive tantrum at the door. It creates a total mess with backtraces, and honestly, it's just terrible practice for on-chain programs. Always, always return explicit errors.
All right, Section 5, testing the entry point.
Okay, so we built the door, we hired the bouncer. Now, we need to try kicking the door in to see if it actually holds up. So what does good look like here? Well, it's a clean compile with an exit code of 0, perfectly mapped unit tests for our instructions, and safely rejecting truncated data, all without ever having to deploy to a live cluster. We can validate the whole shebang locally.
Now, you know it's standard practice to write tests that pass the Hoppy path? Like, sure, sending a perfectly formatted 10-byte payload and getting an OK right back. But honestly, it's way more important to verify the failures. If you send a short payload, your explicit length checks should instantly catch it and trigger a deterministic invalid instruction data error. Because if your program panics right there, yeah, your length checks just aren't tight enough.
And our final step, Section 6, preparing for automation.
These steps we just went through, they build an incredible foundation for the future. By parsing unambiguously with that stable discriminant, using those explicit length checks, and localizing our errors, we haven't just written good code. We've created a highly modular, totally testable entry point snippet. It's clean, it's predictable, and it's strictly organized.
And because we kept this code so buttoned up, it perfectly sets us up for our next lesson. In the upcoming module, we'll be looking at AI-assisted refactorings and pattern automation. We're literally going to use AI to automate these exact repetitive refactoring patterns, stuff like discriminant parsing, length checks, validation stubs, across multiple templates. It's going to be incredibly powerful, but it entirely relies on this clean, predictable foundation we just built today.
Before we wrap up, I want to leave you with this provocative thought. Okay, so we've mastered static length checks today. But what would happen to your checkpoint if a dynamic, variable-length UTF-8 string tried to sneak past your bouncer? Think about how you'd implement safe unpacking for dynamic payloads using length prefixes. It's a really great interim challenge. To dive deeper into that challenge, explore the exact code snippets we discussed. And honestly, just to learn more about advanced Web3 programming, be sure to visit us over at Forge College. This explainer was brought to you by Forge College. Thanks so much for joining me. Keep writing clean code, and I'll see you in the next one.